Our next speaker is Lucia Moura from University of Ottawa and in Canada. And she's going to talk about finite field construction of ordered covering arrays. So thank you for being here and go ahead.
Okay, thanks for inviting me to speak in this very nice session. So today I'm going to be talking about finite field constructions of ordered covering arrays. This is going to work with André, who did a PhD, co-supervisor by me, and Emerson Carmelo from Brazil. And then when he came to the Sandwich in Canada, we also did some work with Daniel Panario and Brett Stevens. And this was my original plan for the talk, but I lied. I lied because I could talk about all of this as in another talk I gave recently, but without going into the finite field constructions. So I'm going to concentrate on the first part of this talk, which I'll be talking about not how to build ordered covering arrays, but ordered orthogonal arrays, and I'll give more details on the finite field constructions. Those ordered orthogonal arrays can be generalized to covering arrays, which are other combinatorial designs. Those combinatorial designs have to do with covering codes on a different type of metric, which is the NRT-metric. So bounds that come from ordered orthogonal arrays and covering arrays can help us with upper bounds on covering codes. This is the third section, would be relating them. But instead of this, I will concentrate on the first combinatorial designs and on finite field constructions for them. The slides have all the rest, so I could share if somebody's interested on the other topics. So ordered orthogonal arrays are combinatorial designs. So the most classical ones are orthogonal arrays. Orthogonal arrays have been known for a long time and studied. They are combinatorial designs that are equivalent to maximum distance separable codes when I'm looking at the Hamming metric. Ordered orthogonal arrays would be generalizations of them, and they are MDS codes when I look at the NRT metric. I'll be talking about this during the talk. They also are related to some other interesting objects called TMS nets. And in this 97, 2002, Rosenbloom-Tsfasman and independent Striganov constructed this ordered orthogonal arrays with certain parameters here that have to do with a finite field of order Q. Then the work that I'm going to talk in here is a similar construction of an ordered orthogonal array with those parameters that uses LFSR sequences in finite fields. And they are objects that cover the same parameter set, but they are different. They are non-isomorph and they have some interesting properties. So that's what I'm going to be talking about next. So we'll start, introducing the basic objects orthogonal arrays. So as many combinatorial designs, they are defined by a soup of letters, and but some letters are more important than others. So let's look at this definition. So I have an orthogonal array with n rows, k columns, alphabet or symbols v symbols, and then a certain strength t. And that strength is what gives the interesting property of the orthogonal array. So here is an orthogonal array with this many rows, 4 columns, alphabet size 3, and my strength here is 2. So I will be concentrating on this lambda 1 because it's too many parameters, but I'm going to be looking at every t columns of pick any t columns, and then you must find every t tuple of the alphabet appearing exactly once. In this case, because t is equal to 2, if I select any pair of columns, let's say this and this, I'm going to run through the array and I will find every pair of tuples of the alphabet there. There are 9 of them, and I find them here, 0, 0, 0, 1, 0, 2. I go over and there is, and this is true for every pair of columns. So that's an orthogonal array. They have been studied a lot. Many constructions come from finite fields. In particular, this one in which you can build, when Q is a prime power, you can build an orthogonal array with Q to the T rows, Q plus 1 columns over the alphabet, Q, FQ, with strength T. Okay, and this is similar to Reed-Solomon code, where you use polynomials to build the code. These are going to be the rows of this array, but then you add an extra. You add an extra column. It's possible to add an extra column. So this is well studied for a long time. So now we're going to be looking at order orthogonal array. So instead of looking at the Hamming metric, which, you know, these are NRT, these are MDS codes in the Hamming metric, we're going to look at another metric, which is the NRT metric. So this is a poset metric. So I have two positive integers M and S, and then I'm going to be looking at partial ordered set, depending on this M and S, that will have size M times S. But this poset is going to be formed by M chains of length S. Okay, so here is an example where I have 3 chains of length 3 in the board there. I have an example where M is different than S. So you remember that M is the number of chains, 4 chains of length 3 in that example there. And I'm going to be concentrated on anti-ideals, which are complement of ideals, and they are sets closed under follower. So whenever I have an element in the anti-ideal, anyone above it must be in the anti-ideal. So there are some different types of anti-ideals. I list them all, the anti-ideals of size 3 here. This T will have to do with the strength of the array I'm going to be building. And for example, I may have everybody in a chain. This is an anti-ideal. I should pick everybody on the top there, right? I could pick the top of one chain plus an element on another. That's another anti-ideal. Or I may have everybody up there. And my order orthogonal array will be defined. The columns of the array would be in correspondence to these elements of this poset. And the locations where I require the coverage of the t-tuples of elements are going to correspond to the anti-ideals of the poset. So instead of requiring that every t-set of columns must have that covered property, it's only going to be the anti-ideals. So this is the definition of it. So again, I have the strength T, symbol set V. My K number of columns is going to be M times S, but the M and S will be important here. They give me the poset omega MS. So if I pick an anti-ideal on the poset and I look at the submatrix whose columns are labeled by those, so I get a subarray of A indexed by the anti-ideal of the poset, I must find every t-tuple of the alphabet exactly once. So when those chains there had all size 1, I am in the case of order of normal orthogonal arrays, but otherwise I have something different here. So here are my chains, and I can look at anti-ideals. For example, this type of anti-ideal, that is everybody in one chain, I look at those columns and I must find every tuple of the alphabet appearing exactly once. So there are 8 tuples, binary tuples here, and each of them appear. If I pick this type of anti-ideal, I also find. If I pick this type of anti-ideal, I also find every t-tuple. And here are all the anti-ideals of size T of 3. If you verify in this matrix, I have this coverage property occurring there. But if I have, for example, something that's not an anti-ideal, like this is not, because whenever I put a 1, I have to have 2 in the anti-ideal, right? So this is not an anti-ideal, then I do not guarantee any coverage. There may be or not. In this case, there isn't, because you notice that the tuple 0, 0, 0 appears twice. So for sure, some other tuple is missing. Okay, so it is a generalization of orthogonal array that has to do with this NRT metric. Okay. So now I'm gonna then show our construction for an OOA that uses finite fields, and it uses LFSR sequence over finite fields. So I have a finite field of order Q, and then a polynomial of degree T. T is gonna have to do with the strength of my array later. So I get T initial values, and then I can look at the sequence formed by using this polynomial as the characteristic polynomial of the sequence. So the beginning of the sequence uses the initial values, and then after that, I have the linear relation using the previous T values to determine the next value related to the coefficients of the polynomial. So these are linear feedback shift register sequence. The sequence is known to be periodic, and the least period always divides Q to the T minus 1. We are gonna be wanting of sequences with maximum period, which are called M sequences. So then we pick that polynomial there to be primitive, right? So if I have a F, an irreducible polynomial that has a root, and that root generates the multiplicative group of the field, then alpha is called primitive, and F is a primitive polynomial. So we know that when the F is primitive, the LFSR has maximum period, and that period is precisely Q to the T minus 1. So there are interesting properties of that sequence. Here is an example for a polynomial of degree 3 over F3. Have 3 initial values, and the recurrence relation given by using the coefficients of the polynomials. And I know that sequence has maximum period 3 cubed minus 126. So this is the sequence. These are the 3 initial values, and then every other value is based on the previous 3. So there's a lot to know about the sequence. This book of Golomb and Gong has many properties of those. Some of them are very important for our construction. So let's take a look at some of them. First, as I look at windows or sub-intervals of length T over the sequence, starting at the first position, and then running through the period, I will visit every T tuple of the alphabet exactly once, except the all zero tuples. So remember, there are 26 here, right? So I have precisely the 26 non-zero tuples, each appearing once. You have 0, 1, 2, then 1, 2, 1, then 2, 1, 1, and so on. You visit every non-zero tuple. So that's a very interesting property and useful for us. There is also something related to the patterns of zeros in the sequence. So if I pick the whole period of the sequence, Q to the T minus 1, and I divide into Q minus 1 slices, in my case here, Q is 3, so I have 2 slices here, then there's a result about the same sequences that, corresponding elements in this slice are a scalar multiple by elements in the base field from the previous one. So this here is twice this sequence. So I'm putting this to one below the other. So I multiply by 2, right? So you get this. If I had another element in the field, I would have another slice, and I'll multiply that by that other element in the field, non-zero. So this means the pattern of zeros in these 2 slices is the same, which is also important for us because patterns of zeros for us will have to do with columns we must avoid to achieve the coverage. And there is also the 2-tuple balance property that I'm gonna use. So let's take a look at the array we build. The array we'll build will build the sequence with a primitive polynomial. And once I have that LFSR, I will first have an extra row with all zeros, and that will allow me to cover the tuple of all zeros that's not given by the sequence. But then here I will pick one of those slices. Remember, my slice Q had size K, Q to the T minus 1 divided by Q minus 1. So one of those whole slices of the sequence I put here. And then I start in the next position, A1, and I put that next slice. So on until the last element of the period, of course it's cyclic, and then I put that slice as well. So I put q to the t minus 1 slices of the sequence, one below the other, below the other. And then this will give us a lot of coverage of t tuples that will be useful for us. Showing you an example for this is t is 3 and my alphabet is also 3. Here is the sequence. This is one period of the sequence. And now it's the same sequence, but shifted by 1. I'm starting here at the first element and now second element, but putting the same sequence, right? Until the q to the t minus 1, and then plus the row of zeros. Pick the slice of size q to divide by q to the t minus 1, and I pick that slice. So that is the array I'm looking at. So that's what I'll be looking at. The two tuple balance property of the sequence tells me this array is an orthogonal array of strength 2, normal orthogonal array, okay, of strength 2. So that if I pick any two columns, every pair of elements appears exactly q to the t minus 2 times. In this case, 3 times. So every pair there appears 3 times, and this is across the board. But I'm interested now in what happens with tuples of t elements. And I'll get to that, but another important thing related to that is this patterns of zeros. Here is the pattern of 0 on the first slice and their shifts, and you see it repeats on the second slice as well as those shifts. And there is an interesting combinatorial interpretation of this. If I consider the columns as points, in this case, for t equals to 3, a projective plane of order 3, each of these zeros corresponds to a line on that projective plane of order 3. I would be calling, the elements being the indices of the columns 1 and whatever, right? And this would have be in one-to-one correspondence to that. And more generally, I would be looking at subspaces of dimension t minus 1 of pg t minus 1, dimension t minus 1 over fq. These patterns of zeros will be important because they will determine when coverage of t tuples do not occur. So I'm gonna get to, this is a result with another student from a few years back. And that tells me if I'm looking at the T set of columns, I want to determine whether I have full coverage of that. Okay, let's just look at back, for example, the fact that I have every window in the sequence of T elements in the sequence give every possible tuple. Well, this tells me that consecutive rows here will visit every tuple exactly once, and then I'll have full coverage. So every tuple, consecutive tuple, I will have the full T coverage there. But in some combination of columns, I will not have the coverage. For example, and this had to do with the positions of zeros. For example, here, this is t equals to 3, this example. So this 0, and this 0 here tells me that in these columns, I do not have coverage. You remember, the zeros should not appear here, already appear there. So I would not have full coverage if I have already this repetition of 0. But that's not only necessary, but it's also sufficient. If I don't have zeros showing up on T columns as a row ever, then I know I have full coverage. And that's what this theorem is telling us. I have full coverage for certain columns, if and only if the columns are linearly independent, and if and only if there exists no row that in those columns I have all zeros. So the pattern of zeros is where my coverage gets problematic. For building the OOA, we wanted select some columns of this array in such a way that I do not have a problem with coverage of my anti-ideals. So I have to be very careful in selecting that. So that's what our result is. So this is the construction I want to talk more about. Now I kind of set the stage. Here, my array is slanted here. So this is the row of all zeros. So you guys have to look at the array. Now here, the sequence is here, right? And these labels here are which columns I chose of that array that I showed you before. So here's the column 0 from that array, 1 and 2. And here in a different order, I'm putting 5, 4, and 3. And I want this, when I look at this to be an order orthogonal array. So how those columns are picked, that's what this theorem is telling us. So the first two, they are placed in sequence in an appropriate way. If you take a look at that example in my board, you can even increase the size of my window if you want with respect to the slides. Those two columns are special, are these first two here, in which I just choose to associate those positions of the anti-ideal, those columns of the matrix, those columns with the columns of the LFSR matrix that I show you, 0, 1, 2, but then I go back 3, 4, 5. So is this two here, I guarantee the coverage of the anti-ideals that involve them. Why? I know consecutive columns give me the coverage. So consecutive columns in the sequence, consecutive positions in the sequence of length 3 in this example, give me full coverage. So if I associate those columns with this anti-ideal, for example, I got coverage for that anti-ideal. But also imagine a spaghetti going around here, right? I either have this 3, or I have 2 here and 1 there, or I have the top 2 and 1 here. All those spaghettis are in consecutive columns in my original array, 0 and 2, or 1, 2, 3, or 2, 3, 4, or 3, 4, 5. So that is fine, this is covered. But now I want to add a bunch more of chains, right? Q minus 1 of those. And then those have to be such that when I look at the anti-ideals there, I do not get too many zeros on those positions. I cannot have anti-ideals of size T that agree with the columns that have 0, or some location, right, on the corresponding columns that hit a pattern of zeros in the sequence. So that is the whole thing here. So how I build those other ones there, I'm going to look at elements in the finite field, the base field, FQ, non-zero. For each of them, I will define a certain K beta. So here in my example, I have a K1 and a K2 because my field has 3 elements. So I look at alpha, the primitive root of the polynomial that I generate the sequence, and this beta is in the ground field. I look at alpha minus beta, calculate its inverse in the finite field. That inverse is some x, but because alpha is primitive, there exists a power of alpha that will be equal to that x, call that power k beta. So that one will be determining the jumps that I will give here on those labels of those chains. For example, in that small case here, I have T3 plus K1. Then I'll associate this with the column 3 plus 2K1 and 3 plus 3 up to TK1. Okay, so it's always going to be TK1, T2K1, TK1. The same for K2. And now what I have to convince you is that I'm avoiding zeros on those anti-ideals there. So the trouble would be, suppose I have a bunch of zeros involving, let's say, suppose I have zeros involving t plus 1. I have a sequence, right, a run of zeros there. I must be sure that when I pick some of those and some of the elements on the other chains, I will not find zeros on those other positions. Or the maximum number of zeros that I find on those positions is t minus 1. I cannot have t of those, otherwise I wouldn't have the coverage. So the whole thing involved studying runs of zeros in the sequence. And then I will try to give you just an idea with some examples to finalize here. Let's look at the case k equals to 1 and look at a run of non-zeros. When I advance in the sequence exactly k1, I will get the subtraction of these consecutive elements appearing here. And then I will get a run of zeros of length 1 less. And then when I do this again, I advance k1 in the sequence, we prove that we will get a run of zeros of size 1 less. So this kind of combinatorics of the run of zeros related for those steps k1 is what is guaranteeing we do not run into too many zeros on these anti-ideals. For example, I would be in trouble if in the position t there, I would have a 0, and then when I advance k1 positions in the sequence and I get here, I will find another 0. And then if I advance more and I find a third 0 actually this is something of degree 4, right? So I start with a 0. If I get another 0, my fourth 0, I would run into trouble. But this is not possible. This is not possible because if I have a run of 0 here, of length 0, the maximum that I can have here is either nothing, right? Like this, no zeros, or I have at most a run of 1 more and 1 more, but I never have all zeros, t zeros appearing in the sequence. So because those are the elements in that chain there that I'm using, k1, 2k1 are these elements, I'm sure this other one is not a 0. So I know I'm running out of time, but basically we had to do a careful study in relating the runs of non-zeros as well as runs of zeros in the sequence to make sure that those selections here of labels would precisely avoid the columns that would have no coverage for the sequence. So I think that's all I have time to talk. Here is André, and this was the first time in the same whiteboard that we have here, when we realized that these runs of zeros were crucial to be able to build the array. This lambda here that we didn't call K1 yet, this is one of those KIs that we realize this pattern that separated these runs of zeros in the sequence that helped us to build the disorder orthogonal array. So that's it.
Thank you.
Thank you.
I really like the picture of remembering the special moment. We have 1 minute for if someone has a quick question. If you want to talk, just talk. And if not, we could have the questions on the forum so we can keep on our schedule.
Thank you.
So thanks, Lucia, again.